Okay, folks, in the last video, did I spark your interest in the alcohol lectures? I hope that I did. Maybe I did because you at least pushed play on the next video. Maybe you weren't really curious about it, but you knew you had to push play because you got to listen to the lectures in order to do well in the class, and I'm okay with that too. If I have to force you to watch these videos in some form or fashion, then that's what I'll do. This is all about education, right? I need to educate you on organic material. All right, so let's start. Well, we left off with this idea of substitution and elimination. And we talked a little bit about electron withdrawing groups. Electron withdrawing groups are these groups like OH that suck all of the electrons through the molecule. That's why we call them electron withdrawing. So there's your OH groups. That's the problem. However, that's their Achilles heel. That OH group, because it is so darn greedy, with the electrons, we can tempt it very easy. So OH groups can become reactive. And just so we're all on the same page, OH groups are going to be regarded as alcohols. Well, if you look at the title of the lecture, they're throwing a lot of functional groups in at us, and the next one is something called an ether. Well, ether is kind of like an OH group, but it's an OR group instead. One of the first functional groups that gets introduced in Chemistry 251. This OR group needs something else, though. It needs to be attached to another carbon, maybe, or some kind of alkyl group. I don't really care what it is. That's why we just write R for random. But you see the similarities there, right? Alcohol is attached to an alkyl group, like a carbon, and it has an OH. And ether is attached to an alkyl group, like a carbon, but instead of an OH, it has an OR. The oxygen is somewhat sandwiched in between two carbons at least. And then we have this sulfur-containing compound, right? So sulfur, of course, is S, but what else is on this molecule? We know it has to be attached to another carbon or some type of other group because it's a functional group. It has to be attached to a larger piece. But what else is on the other side of sulfur? We'll get there when we get there. Most of the time, Chemistry 251 doesn't mention sulfur-containing compounds that much. So this is going to be a new one for everyone. But alcohols, ethers, and sulfurs. Look at the similarities there. So the issue here, like we've talked about in the previous video, is that these groups typically are pretty good nucleophiles. That means they're very pretty. They're going to go in, they're going to substitute another group very easily, and they're going to smack dab on top of a molecule and not leave. Unless we can do something to them. And we can. It requires a little trick. It requires a little baiting, but we can do it. So how do we do this? All right, so here's the organic with an OH group. And if I add on another nucleophile, let's say carbon triple bond N, a nitrile group, nothing's going to happen here, folks. Nothing's happening here. Go home. Nothing to see. Wrap it up. Move on along now. Move on. Nothing. Why? Because the C triple bond N is not a better nucleophile than the OH group. Now, how do I know this? Well, you're going to find some type of nucleophilic chart in your organic text. Typically, this is going to be found in a substitution chapter, and you're going to see a table, and that table is going to have all of the common nucleophiles that are listed. These are not the only ones, but the ones that we see most of the time in Organic 1 and Organic 2, and they rank them in order. Ugliest to prettiest or prettiest to ugliest, depending on the textbook. Wherever you find the NH2, that's the pretty side. So it's just simply a ranking, and I'm going to let you use this nucleophilic chart anytime that you need it. So I'm going to give that to you on a test. It's going to be there. The online assignments, make sure that you have a reference to it just in case you need it. You're taking those at home. So just make sure it's there beside of you. Just make sure that you understand what it's telling you. So OH at this point, the reactivity here is very low. We need to improve the reactivity because there's not too many things that will come in and say, OH, poink, out you go. And that's Mr. and Mrs. America NH2. That's really the only one that can do it. So, as a friend to this carbon, I am going to have to somehow convince carbon that that OH group is ugly. Imagine you and a best friend. That best friend is dating someone that's just a pure, well, you know what I'm going to say. Just no one can stand it. Him or her. And you're like, please, just break up. Just put everyone out of their misery and get rid of that awful person. Not only is it ruining your life, but it's ruining everybody else around you as well. Just listen to us. Well, one of the ways that you can get this carbon to listen to you is to make OH ugly. Now, how do we do that? You give it a lot of fast food. Make it fat. I mean, was that politically correct? Probably not. But you get my drift, right? Wipe the makeup off. I mean, 2 hours of makeup, how much ugly do you got to cover up? So wipe it all off. Let carbon see the real OH that's underneath it. Take the maybe testosterone pills away. I mean, these guys are going out to the gym and they're buffing up, inches and inches and inches of muscle. Well, put something else in the pill bottle. Let them get all flabby. You've got to do something to the attractiveness. That's what all of this boils down to, folks. It has nothing to do with personality. It has nothing to do with if you actually get along with that person or not. It's all about the outside. So the only way that we're going to get a reaction to happen with this alcohol group and any alcohol is to make this ugly. And there's a way that we can do that in a lab. We call this activate. We don't call it make it ugly. That's my term. I just like that a little bit better. But we call it activate the OH group. Well, there's a very easy way to activate the OH group. But we can also activate ethers as well, right? They're similar. ROR, ROH. So activation can happen on the alcohol side. Activation can happen on the ether side. Now, sulfur-containing groups are a little different. With the sulfur-containing groups, they've got a R group on the left-hand side like the others, but we also put a question mark here. We didn't really know what else was coming along, and I said we'll talk about this one a little bit later. What you'll find out is that we don't really have to activate this one too much. This one's kind of ugly. That carbon's not necessarily dramatically attracted to this sulfur-containing group. It could be, but it's nothing like an OH group or an NH2 group or an ether group or some of these other nucleophiles that are out there. So this really dabbles back into the world of substitution. So this is where substitution is going to come back and play. So sulfur-containing groups really goes back to the world of substitution. They're not very attractive. We don't have to worry about them that much, but there are some things that we do have to kind of pay attention to. And that's why we lump them into this category. The OH, the alcohol, or the ROR, which is the ether, those have to be activated. So the question now is, how on earth do we activate these groups? And the answer is very easily, we protonate it. There you go. We protonate the sucker. What does protonate mean? Well, look at the word. Use your words. Use the terms. Protonate, the first part is proton. Proton means hydrogen. That's right, folks. That's all we got to do. That makes it ugly. I just put it into an acid. I could probably do people the same way. Put them into some acid. That sure will make them ugly, won't it? Well, it will do the same thing to this OH group. Put it in some acid. Make it ugly. Then carbon's going to look at that OH group and it's going to go, ew, go away. I don't want you. And it's going to choose another nucleophile that is around, even if maybe it's an ugly old bromine or an ugly old iodine. That's how this process is going to work, and that's all that it's going to take. So H plus, protonate, this typically means, folks, we've got to use an acid. Some type of acid is going to be used in order to make this go forward. Okay, now let's really talk a little bit about chemistry here. Okay. I at least need to prove that I have somewhat of a degree, right? So CH3OH, and we add bromine minus, and we're saying there is a possibility that CH3 would kick off the OH to give us a Br, and then that will force that OH group off. All right, but the problem here is that this is not going to happen. If it did happen, that would be the products. It's not going to happen because the OH group is a very strong nucleophile. Not the strongest, but one of the strongest. So why? Why doesn't this go on? I keep talking about nucleophiles, right? Well, let's just take a look here. You know, the definition of an acid and a base. Very first kind of thing we talked about in Organic 1. The definition of an acid is a proton donor. The definition of a base is a proton acceptor. All right, so if I take a look at this reaction, this OH group here on the product side, this is a base, folks, and it's a very strong base. And we said in acid-base theory that reactions tend to not be on the strong side. Reactions like the weaker side, if they were strong, that's going to make the reaction go forward. So they're going to be on the weaker side of the house whenever they show up. So if this is the side with a strong base, then this is going to be the side with the weaker base, and it is. Take a look at the bromine. So out of these two sides of the reaction, the weakest side will be over here. And that's why this reaction lies to the left. All of that is acid-base theory. Don't have enough time to talk about acid-base theory. I just assume that you know it, which is why I'm only briefly introducing it. But if I could protonate, if I could bring in an H here, then all of this changes. How? How does this even happen? Okay, well, let's take a look. Carbon, carbon, carbon with an OH group. Well, I told you this oxygen's got two sets of electrons on it, right? So there they are. So what if I bring in an acid, maybe like HBr? That's an acid, right? I just said protonate. I just said acid. I didn't tell you it has to be a certain type of acid, did I? No, it just has to be acidic. HBr is acidic. It has a proton. That proton can actually take part in the reaction. How? All right, well, let me redraw this a different way. There we go, HBr. And we have an alcohol group. And now we have an acid. And these two things are going to react. The HBr is polar. That's because Br has all of these electrons here. They're not drawn, but they're understood to be there. We have some polarity difference, which means that this hydrogen is partially positive and this bromine is partially negative. That bromine is sucking those electrons away from the hydrogen bond. So we get partial positive and we get partial negative. All right, well, over on the alcohol side of the house, we've already kind of discussed this as well, right? We said that the OH group is electronegative. It's got some electrons around it. Because of that, this is partially negative, and it sucks electrons away from that carbon, and that's partially positive. So if I bring an alcohol into play, and I have an acid as well in the boiling flask, or the container that I put it in, on a sheet of paper that I write a reaction on, this is what goes on. That bromine is hounding the hydrogen. Gimme, 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 gimme. And that hydrogen says, fine, I'm tired of all of this. Just take it. I don't really care. And while the hydrogen is thinking this, it's looking over here at that beautiful OH group. But it knows that OH group is part of that carbon. It knows the OH group is in a relationship with that carbon, and it just decides to take its chances. And this hydrogen comes close to that OH group, and it says, hey, I know you're in a relationship right now, but would you be interested in going out sometime? And what does that beautiful OH group say? Ha, yeah, of course, why not? See how it treats that carbon? And carbon never learns the lesson. That's just how these organic molecules are. So the OH group is negative, and that OH group looks at that hydrogen, and it says, come on. And that hydrogen says, bromine, I've had enough of you. You've taken everything that I have, so take these 2 electrons and shove it. And now what we have is an organic. And this organic is a carbon, carbon, carbon in this case, with an OH and a new hydrogen that is there. And then we have this bromine that's left over with a negative. We have just protonated the alcohol. That's what that means. Protonate means add a proton. Proton is a hydrogen. We've added a hydrogen onto the alcohol. The problem, though, is that we have a lot of different things that are going on at this moment. First off, I want you to understand that I'm drawing just these carbons, but they're actually hydrogens here as well. So that needs 3 more, this one needs 2 more, and this one needs 2 more. All right, everything has to have a total of 8 electrons around it for the most part. So CH3, CH2, CH2OH. That is a shortcut that I'm leaving off because I just assume that you know that they're there from Chemistry 251. The other thing that I quite honestly do that I shouldn't maybe do as much is that I like to leave off charges. That's just because I know that they're there, but you might not know that they're there. So I will try to catch myself every single time that this happens. And right now I'm leaving off a charge. And that charge is on this oxygen. That charge is going to be a positive. Well, how do I know that? Well, this goes back to formal charge. Formal charge was discussed in Chemistry 251, probably the very first lecture that you get when you talk about general structure. That oxygen has a total of 6 valence electrons. And we're going to take 1 away from that bond, 1 away from that bond, 1 away from that bond, and 2 from the dots. So 6 minus 5 is a positive 1. That's how formal charge works. So that is a positive oxygen at this point. So here's the problem. Oxygen decided to get almost in a cheating mode where it's seeing the carbon and the hydrogen at the same time. And then, if you look at it, it's probably married too, because it brought in the hydrogen with it in the very beginning. So this oxygen finally makes the decision to say, seeing 3 people is just way too much. I can't do this. I'm overloaded. I have a positive charge. I'm going to have to get rid of something. So this oxygen looks at these choices and it says, which one can I get by with sucking everything that I can away from the bank accounts? Which one's going to be the easiest to bully around and let me do what I want to do? Well, hydrogen is just little old puny thing, and that other hydrogen is just a little old puny thing, and then that carbon is a little bit bigger. It has a little bit more electronegativity with it, a little bit more spunk. You know, when I ask for money, it doesn't give me all the money that I ask for. Carbon fight backs a little bit, and it says, you know, carbon, that's it. I'm starting to lose interest in you. You're not giving me all of the money that I think that I deserve. And it takes this bond and it begins to break it. And it breaks the bond and away it goes. All right, now before carbon fully lets that happen though, that carbon is going to look at this and say, well, if you're leaving, then that means I'm freed up. I'm single again, and I need someone in your place. And it looks out into the bar, and it says, hey, ugly bromine, why don't you come over here and let me get to know you a little bit better, because you're the only one left, and it's 2 a.m. at the club, and I got to go home. And bromine says, okay. That's exactly what it does. This bromine, which is negative, which is labeled as the nucleophile, will come in and it will go to that carbon and it says, okay, I'm here. Let's have a relationship. And that carbon says, all right, oxygen, I'm done with you. You go home with your 2 little old hydrogens, your 2 little old friends that you made this evening. Go away and leave me alone and never come back. So what we end up with at this point is a carbon, carbon, carbon with now a bromine on it. And then this OH group took the other hydrogen. And folks, look at what that makes. That makes H2O, water. So in order for this to happen, in order to get this alcohol to work the way that we've explained it, first, you have to have an acid. These take place in acidic conditions. You have to have it. Next, you typically have to have a little bit of heat into this reaction as well. You know, you've got to kind of persuade OH to go ahead and leave. OH is going to kind of tough it out when it can. Even with that extra hydrogen, it's going to try to make something work, but it knows it's just fighting a losing battle. So if you put in a little bit of heat, you make this step a little bit faster. And we don't want to wait around forever for this to happen, do we? No. So the little bit of heat goes ahead and it gives the oxygen the courage enough to say, fine, I'm gone, I'm out of here, I hate you, I'll never see you again. And OH goes off with the other hydrogen to make water. Folks, at its heart, this is kind of like a substitution, isn't it? I've just substituted something. I did have an OH group in the beginning. That OH group is right here. And now I've substituted that in a way with bromine. That's kind of surprising for an untrained eye, because you're like, how does that OH group leave? I thought OH group was pretty. I thought OH group was really high on that nucleophile list, and it is. But the addition of the acid makes the OH ugly. The true colors begin to show from that alcohol group. And that's all that it takes. And that's all that carbon needs to help make the decision to stop that relationship and bring in whatever else is in the arena or whatever else is in the bar to that carbon. And we play the game of switcheroo. OH gets switched for the Br group. Now the question is, what type of alcohols undergo these reactions? This kind of goes back to chemistry 251 again. We have a couple of different alcohols. You know, we could have an alcohol group that's attached to just one carbon. We could also have an alcohol group that's attached to one carbon that's on two others. And we could have an alcohol group that's on a carbon that's on three others. All right, so we have different terminology for this. Let's do a quick review. The OH group on a carbon that's attached to only one other, this is called a primary. The OH group on the carbon that's attached to two others, this is called a secondary, go figure. And the OH group on a carbon that's attached to three others, guess what? This is a tertiary carbon. So there's differences between the alcohols that we'll see in these reaction schemes. And if we take a look at the rate or the speed at which these reactions happen, primaries are going to be the slowest. Secondaries going to kind of be in the middle, and tertiaries are going to be the fastest. In the beginning, right now, the only reaction that I have introduced to you is the reaction with an HX. And that X stands for a halogen. So this is HF, typically not very used. Fluorine's very explosive, hard to handle. We just don't like it. Electronegativity is very high for that one. HCl, HBr, and HI. Iodine, we can use it. Quite honestly, iodine is very large. It's very big. I call it very fat in a way compared to some of the other atoms because the atomic radii is so huge. So that HI, the iodine sometimes has a really hard time getting into that molecule and attaching to the molecule just due to the physical size of that atom. Whichever way, though, these are acids. They have the hydrogen. They protonate the alcohol group. And out of these choices, HCl and HBr are going to be the most commonly used. And there you go, folks. There's your first alcohol reaction that we have introduced. Something else that I want to say, because we keep mentioning substitution, I do want you to keep in mind that SN2s, which are the cheaters, and SN1s, the carbon breaks up first and then takes on a new partner. The SN2s, the cheaters, are really just primary only. It's very easy for this carbon to cheat because there's not too many neighbors beside of the house, right? That carbon is just carbon. It's only attached to one other thing. That's it. So this carbon can cheat very easily. The SN1, this is where the carbon really cleaves it first and then says, okay, I've been by myself for a little bit. I'm ready for a new relationship. That SN1 happens with secondary and it happens with tertiaries. So just something to keep in mind as we go further into this lecture series. All right, so that's where this video is going to stop. Hopefully I didn't scare you off with your first alcohol reaction. Hopefully now, again, like I always say in Chem 251, you'll look at a bar atmosphere a completely different way, and you'll start pinpointing, gosh, that person thinks they're an alcohol group. That person thinks that they're just an olamine, right? Who does that hydrogen think that they are? I mean, it's the whole concept of bar chemistry. And I just think that people relate to it a little bit better when I do it. Okay, so that's where this video is going to stop. In the next video, we'll pick up from here, and we'll talk more about alcohol reactions. Stay tuned.